and then we've seen the AVL. Okay, we've seen the binary search tree, an AVL, and then now what we're going to be seeing, the heap, which is some kind of a tree, but it's a different type of organization of the data in it. Now this heap, let me just go for the slides, and I think this is the one. Now this kind of, now the AVL is like a binary search tree that is sorted from left to right, and the left is smaller than the node, the right is bigger than the node. Now there's this kind of right-left sorting of a tree. Now there's another type of sorting which is up-down, which means we'd like, for example, the parent to be greater than the child, or the opposite, the child is smaller than the parent. So every parent is going to be either, let's say, if there's like this two type of heap, max heap or min heap, but this is not recursion. I was looking for the tree. So in the heap, the organization of, the sorting is going to be vertically, as opposed to the AVL where the sorting was some kind of horizontally. By horizontally, you mean like from the left, the left child and the right child are going to be sorted based on the head, the parent. Now let me show an example. Now we've done these deletions, etc., but this is the binary heap. Now this is the binary heap, is a tree that has the value of each node is greater than or equal to the value on each one of the children. Like, for example, this is a type of a binary heap. As you can see here, this is bigger than any one of the child. This one also bigger than any one of its child. So that's the idea of this is a binary heap. And this is not a binary heap, because now this is not like, there's no sorting. Now this is an example of a max heap, which means the maximum is on the top. The min will be like the opposite when we put the minimum on the top. So that's the main idea. So the tree is perfectly balanced, and the leaves in the last level are all in the leftmost position. Let's talk about the first part. The tree is perfectly balanced. Remember what this perfectly balanced means? What does this mean? The tree is perfectly balanced.
The number, the right and the left is same.
The number of the right and the left is the same. That's how we know it's perfectly balanced. Yeah, it's not more than the difference between the height is not more than 1. So we can have something like this, which is the difference is not more than 1, or like this, for example. This is also difference is not more than 1, but what they said also is that, so this is the first part. So it's not more than, you cannot find, it's not an unbalanced tree. And the other thing is that the leaves in the last level are all in the leftmost positions, which means when you add here, you see, you add, for example, imagine that this 6 was not there. If you add 6 to this here, it will be, you just add to the left. You start from the left to the right. So imagine now, let me just maybe show something, I don't know, like this one, like this, for example. I don't know, it's, so if you'd like to, as you can see, they're all sorted from the left to the right. When you add something, it's going to be added in the last one to the leftmost position that is available. So for example, I'm adding 15. This is the last one, whatever, it's going to be the last one here. But then this 15 is going to move up, but let's not focus on that. The idea is that this is going to be on the leftmost position, which means when I'm adding a tree, let me just maybe, I feel like I haven't explained it clearly.
So you can add from the left to the right?
Yes, we always add from the left to the right. So for example, I add 1, this is the one going to be here. When I'm going to add another one, it's going to be here. another one here. Now if I add another one, it's going to be here. Regardless of where, we always start by putting it here. Always, from the left to the right. That's how we feel it. So when you add a new one, even if it's like this, I'm not going to add it here because it makes more sense, whatever. This is not like that. When we add it, it's going to be always from the left to the right. Left. And I mean, we're going to the leftmost position. Every time we keep adding to the left until we fill the level, and then we go back until the left. Yes?
So the number should be ordered.
The number should be ordered. Well, we talk about that. The ordering, the way we order them is going to be different. I mean, there's something that we need to do to keep them always ordered. But the insertion, every time I insert at the bottom to the left. And then I'm going to find later on, do something to find the correct position of that number. So that's what this means. And this is a max heap. If we present greater by less than, which means now the value of each node is less than or equal to the value stored in each of the children. That means the one on the top is smaller than the one on the bottom. This is becoming a min heap. And a max heap is the biggest on the top. And in the binary heap, the ordering of the children nodes is not important. The order of those nodes in the bottom are not important. What's important is the order of like the levels. So that's what's important. Now again, this is suitable for priority queues because let's say if we would like to insert things in a queue and would like to dequeue only the ones that have the highest priority first. So this implementation will allow us to always have in the head the top priority ones that needs to be dequeued first. And that's why the heap is a good implementation for a priority queue. It's mainly used for that. And it doesn't matter if this is going to be this one or that one. It doesn't matter now for this time because what we're interested in, just put the maximum on the top and sort them based on the maximum value. So each level is going to be like bigger than whatever is below it. That's what's important. And that's why we can have, for example, a different type of queues depending on the values. Sorry, not queues. Different type of heap of trees. But all of these are going to end up having the 10 to be on the top. And when the 10 is going to be removed, dequeued, now the 9 is going to take its place because of the process that we're going to see, inshallah. Now, because of these kind of rules, this tree can be easily implemented using an array. And that's one case, one scenario, when the array will be easier implementation for a tree. One dimensional is enough. Well, you can organize them in 2 dimensional, but 1 dimensional is easier. 2 dimensional would be more complicated. Like how will this work? Well, let's see. Because we're always adding to the top leftmost on the child. That means it's going to be the end of the array. And we're always going to find, because we do this, it's going to always be like the first one is the head. So this one is the root. I'd just like to change this to red. So this one is going to be the root. And then, so this is the root. This is the first level. This is the second level. And so on. Because we know it's a binary tree. So the first level is going to be 2. The other level is going to be 4. And so on. Yes?
So the insertion here, is it level by level?
Now when I insert, I always insert to the top leftmost in the child. That's when I insert. Then later on I do something to find the correct position for that. I'll talk about the insertion. But now just let's talk about how this is going to be represented. It is going to be represented using an array because the root is always at the first position and the parent of any element is going to be using this formula. Like for example, the parent of this one, so what is the the index of this one. This is 0, 1, 2, 3, 4. That's why you can see that this 4, I have this 31. And now this is array of 4. So who's the parent of array of 4? The parent of array of 4 is 4 minus 1, that's 3, divided by 2, that's 1, and this is going to tell me this is the array of that one. So there's some kind of rule to find the left child, which is of this one, of this I, the left child of this one, like this 4. What's the left child of this 4? So let's find 4, 5, 6, 7, 8, and 9. So there's always a rule. The left, this is going to be 2 times plus 1. 4 multiplied by 2, that's 8, plus 1, that's 9. And the one that's on the right, well, plus 2, because it's one more. And that's how you can define some kind of a result, a relationship between the different indices of an array with these things. So the array implementation is going to be easier, and because there's some kind of this rule like that. So that's the talk. Are you okay with this? So the first one is easy to understand, right? Because it's the first one. Now the second one is that the rule is that the parent of any element is going to be following this kind of rule. Now let's have a look. For example, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's find what is the parent of this one, this 24. If I'd like to find its parent, what I need to do, this 24, I need to just take 1 from it and divide by 2. The index of 24 is 3. 3 minus 1, that's 2. 2 divided by 2, so that's 1. So this is going to give me the index of this one. Let's find this one, for example, or 8. Or what is the parent of 8? So 8 minus 1, that's 7. 7 divided by 2, 3. And that's where I can find it. So there's always this kind of relationship. And if I'm looking for a child of anyone, for example, the child of this one is going to be 2 times plus 1 or 2 times plus 2. So 0 times 2, that's 0. Plus 1, this is the first child. Plus 2, that's the second child. Like this one, for example, the first child on the left one and the right one. The left one is 2 times plus 1 or 2 times plus 2. 2 times, that's 4, plus 1, that's 5. 4 plus 2, that's 6. And there's this rule that can be applied to any one of them. 2 times plus 1, 2 times plus 2. And that's from any node, you can find who's the parent by just taking 1 divided by 2. And you can know who are the childs by multiplying by 2 plus 1 or plus 2. So, and the last non-leaf nodes, these ones, the last non-leaf nodes in the array is going to be the count of what? How many elements? How many elements do we have? How many elements do we have? 9? 10 elements from 0 to 9. So that's 10. So 10 divided by 2. 5 minus 1. That's 4. And it shows us 31, which is not right. So what is this? Well, this is the last parent, not the last index of the last row. It's the last parent because this is the last parent. This is not a parent, so the last parent was this one, 31. That we can find by just counting how many elements do we have, divided by 2, subtract 1. Do you have to memorize this? Well, I think you can find them. You don't need to memorize them. But this is just to show you that this type of tree can be implemented using an array, and it will be able to store, and you can find and navigate and traverse the tree very easily just by following this kind of rules. If you'd like to find the in order, or if you'd like to traverse the tree, then this is easy to implement. All right, so we said that this is good to implement as a priority queue, and well, let's talk about now when we would like to enqueue. What happens? We enqueue and dequeue. Now let's say we have this tree and we'd like to enqueue this number 18. Now let's see how the implementation works. First of all, when we enqueue an element, we just put it at the end of the heap, which means we always put it at the end. That's the first thing. And then, while this element is not in the root, and that element is bigger than his parent, we're just going to swap this element with its parent. So what we do, we insert at the end, and then we check. Are we at the root, or... So that's the first thing. Are we not on the root yet? That means we're still not on the root. We can just do... We need to do something. Because we're not in the root, so that means we need to check if we need to go up or down. I mean, we need to go up in this case. Now, how do we need to check? We just check this one with its parent, its immediate parent. And we can know that because of this relationship. We know which parents from who, which the parent of an array. We just do this and we find its parent. And then we check that with this parent, which one is bigger? Now, in this case, look at this kind of organization. This is a min heap or a max heap? Well, this is a min heap because the top is the smallest, the bottom is every level is bigger, smaller than the level that is before. This is below it. So that means now we just put in the smallest on the top. So we put the first element, the last element that we insert at the end of the heap, and then we check. Do we need to swap? If this one is smaller than this one, yes, we need to swap. Then we swap the parents. And this is called percolate up. I don't know why they call it percolate, honestly. I have no idea. They should have used swap. I would use swap. But why this percolate? I have no idea. But anyways, percolate means swap. So we swap the 18 with the 31. And then we're just here now. We're here now. After swapping, we're not going to stop unless we're either at the root or this one is not smaller than the parent. But this is still smaller than the parent, so we're going to be swapping them again. And then this is going to be we're either at the root, we're not at the root, and then is this smaller than the parent? No, we're not, so we're going to stop. And this is how, after enqueuing, you just put that element in the correct position so it can be at the right level based on its priority, based on this level, this value. Is that okay? So this is not that complicated, but just need to know how this works. If it was like in a max heap and in Q15, same idea, you put it at the last, and then you see this one bigger than this one, then yes, you swap. And then where are we? BC. So then this one is bigger than this one, we swap again until we cannot swap anymore, or we reached the root. That's how this works. And when we dequeue, well, we always dequeue from the head. Now when we dequeue from the head, because this is basically it's a priority queue, we just always dequeue from the top. So the root is going to be gone. And what we do is just we take the one on the top, the last element in that heap, and we put it in that place. And then we try to find its position by swapping down, or that's what they call it, percolate down. So when you delete from that priority queue, or from that heap, you delete the 13 because this is a min heap, right? So we're going to put this last one up, and it ends up like this. And then we compare. As long as we still are not in we're not a leaf, we're going to keep comparing. Is this one bigger? Because again, this is a min heap. That means the minimum is going to be on the top. So if this is bigger than the child, we're just going to swap them. I'm sorry? I only dequeue from the root. Yeah. No, because this defines generally if it's a priority queue, you would like to dequeue based on that priority. So I'm not going to be putting something that has a less priority than other one. So if it's by priority, it means this one has higher priority. You cannot dequeue this one before the 13. So that's why the dequeue is going to always take from the root. And then we try to find the position of that. Now, there's something here. When I'm going down, I'm comparing. Now I have two options. Should I compare from one to the left or one to the right? Because I can just compare these two. Which one should I compare with? To the left? Always? Then why we do that here? Why didn't we just you find the minimum from the children? We look before we can swap down or percolate down, we're not going to choose anyone, left always or right always. We just look for the minimum of these and we swap with that minimum. Very good. So we take this from these two, the 18 is the smallest, so we're going to swap it with that. So that's why when you have the queue, you extract always the element from the root. Then you put the last element from the leaf in its place. And then you remove that leaf, I mean this one basically. We remove this one. Remove this one. That's what it means. After that, we just start from the root, and while this is not a leaf and the root is smaller than any of its children, so we'd like to find which one is the smallest, then we swap this with the largest children. Well, basically this is like a max heap, because this with the largest children, this is a max heap. And actually the way this is done is kind of confusing, because sometimes they put a rule for the max and then the example is for the min. So in this case we'd like to look for the smallest. If it was a max heap, we look for the biggest, and then we swap. We swap until either we're we're a leaf or there's no need to swap. Like for example here, where we're after 21 here, the 31 is displaced. There's no need to swap it with 32 because there's only one. And that's how you're going to be always maintaining a priority related queue. What time is it? I'm seeing some eyes getting down, and if you want to wash your face, that's a good time. Yes. So if we look at this example here, this is going to take the 20, for example. So we dequeue, and then what is going to happen is we take the 6, put it in its place, and then we find which one is the biggest from the children, and then we put it up, we swap with it. And then this again, we find this maximum, and then we swap with it, and which end up with this kind of queue. Now the way we insert, we build the queue, this kind of a heap, there are two ways to do that. Either you build it top down or bottom up. Different ways how to do that. So in a top down, we insert at the first time when it's empty, we always insert this top down, because there's only one, so we just insert the first one. And then after that insertion, if the heap property is violated, which means this relationship of smaller or bigger is violated, we just do some kind of swapping or this percolating. So let's look at this example. We insert 4, and then after inserted 6, we put it here. This is a max heap, so the maximum is going to be on the top. So we insert this 4 in the beginning, there's nothing to do, and then this 6, then we swap, because they need to swap. Then we insert 10, for example, and then this 10 is going to be on the leftmost, always, all the time, and then if this is bigger than the parent, we just swap. And then we insert 20, so 20 is going to be in the leftmost part, and then we're just going to be swapping the 20 with the 4 and the 20 with the 10, and that's how this works. And if you insert 8, or 8 does not need to be updated, I mean to be swapping, so we just, this is how it works. You keep inserting, and then you percolate to after each insert you make sure that your heap is still sorted. Now to not get dizzy, you have to, now let's look at this into this max heap, and then we insert these values, and we watch the values inside of how these are going to be inserted into the array. Now the first value, always the first position, not a problem. But then we insert this 8. 8 is going to be at the bottom, and then we're just going to swap them, percolate up. And so we put it this way, and then you flip them, and then you insert 6, nothing needs to be done. Then you insert 1, nothing needs to be done. Then you insert 10, well, now we need to swap. So you go for the parents, so 10 and the 2 are going to swap together, and then the 10 and the 8 are going to be swapped up. So the percolating up is going to put that into the its final position after the insert. So you insert, you check until you find it's in the position. That means it's not, depending if it's a max heap or min heap, you find it's not bigger than the one on top of it, or not smaller than the one on top of it. Basically, if it's a min heap or max heap. Okay, I'd like to, just so we can not get too much into the details, I'd like to look at the examples here. I would like you to be, for example, building these. So I would like you to wake up a little bit and stop just listening to me and doing something. Let's just insert this using this top down. But what is the bottom up method? Because we just saw a top down, and the bottom up method is this way. Let's have a look at this example, and then we go to the practical part. Oh, you know what? Let's just do this first. So because I'm seeing too many eyes that I'm getting sleepy. This with this top down, and then we'll do the same with the bottom up, inshallah. So let me just free you for that. I'm sorry? No. Now we said that this top down, we understood how it works, and now we just add and then swap whenever we need to. This is not really a very efficient method, this top down, because we always put it in the bottom, and then we always try to find the position, and we most probably going to result in some kind of percolation or percolating, swapping like upper to put it back into position. Now imagine if it is a big size, then it's going to take a lot of time. Now this bottom up approach is much efficient, but it works differently. Now how does this work? Let me just show this to you with an example. Now we have these values. The first thing, we just put the values regardless of the sorting. We just put the values into a tree, and then we run this bottom up approach, which is going to do what? It just starts with the last node that has a child, the last non-leaf method node, and then we just percolate to put the minimum on the top. So now, for example, after inserting all the values, regardless of we're putting them into the position one by one, we put them all, and then we sort them by doing this bottom up. While the difference between the bottom up and the top down is that we put one element at a time and we sort them immediately afterwards. The bottom up is doing actually put them all and then sort them all. And the way we sort them is like this. You just go for the last node that is a parent and you sort it. Now this is a min heap, so minimum up. So we put 31 first, and 32 down. So this is what happens here. Then we keep going from the other one that is the one before the last node that is a parent, and then we keep going up till the root. So let's just see what is happening. So this one, it was done, we resulted in this thing 31 being up. Now the rest is going to be the same. First of all, I just would like to make sure that we inserted all the data the same way we do. 70 is the first one, I just forgot to mention that, and then 29, 68, and then 65, 32, 19, 16, and then 13, 26, 31. We just always put them until the end from the left topmost, and we go this way. So that's how we insert, regardless if it's bottom up or top down. But for the bottom up, we just insert all the data first and then we sort them later. Now with the sorting, we just keep going until we find where we go up to the root. So we put this and then we swap, we check the other one, this is the next one, which we find which one is the minimum, we swap it, so that's why we're going to find the 13 going up and the 65 taking its place. And then we keep going. Now this is the other one parent. Then we put the minimum is going to go up, so that's why we have 16 here and 68, and then we keep going. This is the other one, and look at here. Now this is a case when we have more than one level, and when we have more than one level, what we're going to look at is finding the smallest, and we just put it up. In this case, the smallest is 13, right? It's immediately after that, and then we put it up. And
it's usually going to be one of the child.
I'm sorry?
The smallest one, the oldest one of the child is 29.
Well, one of the immediate child, you mean? It can be here because we inserted the data without regardless.
But we sorted before, so
we don't sort here. With the bottom up approach, we just put them.
before in the second step.
65.
Oh, you mean, yes, in here.
Yeah, and here.
Yes, you're right.
So
That's true. Yeah, you're right. So basically, when you're sorting this, you're right. We're focusing mainly on this one with these parents. You're right. So it cannot be this like the minimum being here, because if it was here, it would have been taken part of this kind of checking here. That's true. So basically, it's immediate child. Yeah, that's something I was not mentioning right. And then now what we have, this 13 is going to be at this instead of the 29. But what happened here? Because when we put this 13 to 29, now the rule is not maintained. So when we have such a thing, we need to go from that until we compare each one from the children of each node after we swap. So now we swap this 13 and 29, but we need to also keep swapping until we find that 29 should be actually at the bottom. So it's a recursion basically that is going to keep checking until we find the end. And now when we have this 70, after swapping this, we just compare 70, which one is the minimum? That's 13, so we put 13 here and 70 here, and then which one is the minimum? So 26, so the 70 is going to go here, and then which one of these two? 29, so 70 is going to be here, and then 29 here, and 26, and 13 is going to be at the top. So this is another approach on how to insert the data. Now I'd like you to, since we are still fresh with this example, do this same insertion, but this time bottom up. And let's see if we can do that. The result should be the same or similar. It doesn't have to be exactly the same, because we don't, maybe it's not going to be the same type of ordering in the same level, but on top of, I mean, the structure should be the same.